In this problem, we are asked to specify the resistors in this current to meet the following design criteria. And the boundaries that we have is that our initial current, Ig, is equal to 1 milliamp. So this current right here is 1 milliamp. We also have our voltage, which is represented as Vg, and this equals to 1 volt. And then we have the currents here. I1 is equal to 2I2, I2 is equal to 2I3, and I3 is equal to 2I4. Before we start this problem, I'm going to convert our current into amps. There is a conversion table linked below in section 1.2 of the notes if you don't know how to do this. But to convert this from 1 milliamp to amps, we're basically just going to put 1 right here and multiply this. 1 milli is equal to 10 to the negative cubed. So we'll have our 1 milli down here so that they cancel out. Then we'll have our 10 negative cubed up here. Our m's will cancel out, and then we're left with 10 to the negative cubed amps. So this is what we have for our amps. Our voltage we know as 1 volt. And now we can start plugging in our currents. Plugging in our currents, we're going to use Kishkoff's voltage law, and that is that the current going into a node is negative and current going out of a node is positive. So if we look at our initial current, we're going to use this node right here. It is going into it. So we are going to have a negative 10 to the negative 3 amps. And all the currents going out of it are going to be positive. So we have this I1 current going out, and we have these I2, I3, and I4 currents going out. So we're going to have a plus I1, plus I2, plus I3, plus I4. In chapter 3, again linked in the notes below, we can also say that our total current is equal to the individual currents in our system. Since it's being broken up through resistors, all of the currents that are flowing through these resistors need to equal our 10 to the negative cubed power. That's just a different way of explaining it. So this is what we have so far, and now we can start plugging things in here. So we have our 10 to the negative third is equal to 0.001, and then we have our i's in here. So our I1 is 2I2, our I2 is 2I3, and our I3 is 2I4, and lastly our I4 is just I4. What we can do is combine these together. So we're going to get a 3I4 here. After we do this, I'm going to move down to the next line. And for this I2, I'm going to plug in our I2. We know that our I2 is equal to 2I3, so I'm going to have that in here. And then we're going to do the same thing for this I3 here, where we're plugging in 2I4 since we know what that is. And then we're just adding our 3I4 to the end. Now we know that this is going to be 4I4, so we can add it to this 3I4. So here we are going to get a 7I4. After we do this, we can go on to the next line and plug in our I3. Now our I3 is 2I4, so we're going to have 4 times 2I4 plus our 7I4. And if we do this, we get an 8I4 here. 8I4 plus 7I4 is equal to 15I4. If we plug this into a calculator, because one note will give us a extremely rounded answer that will make our final answers off, we get 0.000067. And this is what our I4 is. If we multiply our I4, as we have to do right here, we're going to get that our I3 is 0.00013. And if we do the same thing here, where we take 2 and multiply by I3, we are going to get this 0.00026. And lastly, if we take our I1, which is 2I2, we are going to get 0.00053. So these are all the currents flowing through these resistors. Now all you have to do, since we have this voltage right here, and voltage is the same across a parallel circuit, is just plug this into our formulas for our R1, R2, and R3 and R4s. We know that we have the equation voltage is equal to current times resistance. All we have to do is modify this so we get voltage over our current is equal to resistance, and that is how we find our resistance. To find the first resistance, we're going to take our R1 and we'll set it equal to the voltage divided by our current of 1. If we do this but include more of the actual 3's, because this is just a rounded answer, we are going to get 1,875. And then we just continue doing this for R2, R3, and R4, where we take the resistance that we're looking at, and then we plug in the current that we are also looking at. The R1 and I1 are linked, so if we do R2, it's going to be R2 and I2, and then if we do R3, it's going to be R3 and I3, same thing for R4. The only reason why voltage does not change is because, again, that voltage is the same throughout an entire parallel circuit. After we plug all of our values into a calculator, we're going to get these answers. And that is it for this problem. If you found it useful, leave a like. If you have any questions about this material, leave them in the comments below. If you want to practice more problems, there will be a playlist also in the description with more introduction to circuit analysis.